Okay, so let's get started. First of all, you have an assignment due today, the vocabulary. About half of you have already turned that in, so thank you for that. I have also posted a Chem 100 assignment, Chem 101, not 100. And that is due next Thursday. That's on pressure that we talked about on Wednesday and a little bit on the gas laws we're going to talk about today. I'm working on putting together a second assignment that is going to be due the following Sunday. And that's going to be using these various gas laws. That's the bulk of what I want you to know from this chapter. I'm going to spend a little bit of time next week talking about the last few sections, but most of what I want you to know is in that first couple of sections, just using the gas laws. Next week's lab is on calorimetry. So probably on Monday, we'll divide our time between a little bit of gas stuff and a little bit of calorimetry so that we've got a little bit of an introduction for the lab. Okay, and then don't forget that Monday you can get extra credit if you're wearing a costume that is science related. Puns are okay, working with other people is okay. Sometimes people will come in and like each person be a different atom in a molecule, so that will work. Just so you're prepared for what is apt to happen, Dr. Fraley wants to see all the costumes, so he'll come in, he'll bring his camera and make sure he gets a picture of you. And if you want the extra credit, you have to be able to stand up and tell people about your costume so that we can understand why it is a science-related costume. Because I'm not really expecting you to like, go and get like the Einstein thing from Amazon or whatever, just homemade costumes are par for the course. If you show up with a piece of paper and a pen scribbled on it and you just hold it up in front of you, please do not expect to get full credit for such efforts. So any questions about the logistical stuff? Okay, so we are going to be working in groups today. And so I'm going to have the two of you come join this table. And then I am going to have Alex join your table. Alex is on the computer, so I'm going to bring my computer over there. So that she can kind of see what's going on with the group work. So we're going to be working with the related gas laws. So I'm going to go over to this board over here. So section 2 goes through all of the pairs of relationships. So we have looked at the ideal gas law that has everything in it. These laws have names after different scientists. You will discover in your reading that sometimes they're named after people who didn't really have a lot to do with their discovery. And I don't care if you remember who, what name goes with what. What I care is that you know these relationships. So one of them gives the relationship between pressure and volume. And you'll notice this one looks a lot like our dilution equation, except instead of molarity, it's pressure. And then we have pressure and temperature and volume and temperature. Those look similar to each other. So these three can be thought of separately if you hold the third thing constant. So if I'm looking at this one that's volume and temperature, I would be holding pressure constant. In each of these cases, it's important that we are using Kelvin. So if you think about what if we were doing this at 0 degrees Celsius and I tried to plug in a 0 here on the bottom of a fraction, my calculator would not be happy with me on that. So it doesn't make a whole lot of sense to do that. And if we used a negative number, then we'd end up with a negative volume or something like that. So we don't want to have those kinds of things happen. So we need an absolute scale, and Kelvin is our absolute scale. Now, pressure and volume, all the scales are absolute. There are no scales where you have a negative volume or a negative pressure. And so you can use any unit you want when you're using these. If we take these pieces that kind of look like each other and combine them together, we get this over here. So you are going to do several mini experiments. And most of you have a micro vacuum apparatus. I only have 4 of them though, so one table does not. So you've got a bell jar, and you've got the bottom here, and they fit on top of one another. This can easily come off. And then you have a syringe with some tubing. The long side of the tubing is going to go into the little hole here. Now, one of the vacuums, the hole is on top instead of on the side. But otherwise, you just stick that in there. And then this usually is a 2-person job because you have to have one person kind of holding everything in place so that we don't get little leaks in it. And then another person will pull out the stopper on the syringe. So on this syringe, this tubing has some valves here. These 2 things are valves. And this is going to allow air to move from the bell jar into the syringe, but it won't let it go backwards. So when you pull the syringe out, the air moves this way. But then when you push the syringe back in, it can't move backwards through that valve. So it's going to go forward through this valve, and that valve is going to push air out into the air. So that's the one-way system on that. So you're going to be investigating I think Frankenstein for most of you. You're going to use the PEEP on that one. And that's because it's a little bit easier to see what's going on when you have the color on it. If you just use a marshmallow, it's a little bit harder to see what's going on. The sugar crystals do sometimes get into the edges here. So if it doesn't seem to be working, you can either take a tissue. There's sometimes tissues in the baskets on your table, or there are wet wipes up here. You can wipe it out, and that might make it work. If it's still not working, I know a couple of these, some of these are like 10, 12 years old, and the O-ring is just starting to crack a little bit. If I put some grease on it, it will help. So those are things that we can do for that. So you're going to do your PEEP, and you're also going to do a ping pong ball. The ping pong ball is going to be very boring, but think of the ping pong ball as a rigid container. And then if you're waiting around for some of the other things to do, the boxes also have some other little toy in it. You can see what happens when you put this in the vacuum pump. At any time you can do I think it's the first one, the marshmallow in the microwave. You have a cupcake holder that you're going to put marshmallow in, and that way we don't make a mess in the microwave. Microwave isn't going to let you put in 10 seconds, but if you hit the start button, that does 30 seconds. Just kind of watch it so that if it goes, really big, then you go ahead and open the door and pull it out. All right, the last thing I want to show you is the fire syringe. So this is our fire syringe from the past. And I don't know where the other part is. There are a couple of black rubber rings around here. And the last time we did this, the ring kind of got folded up onto the stopper. And so now this won't move up or down because it's kind of out of place. So we bought a new one, but I'm just going to use this to fold up to show you. You're going to pull this stopper out, and you're going to put just a little bit of cotton in there. And you want it to be really kind of fluffed out, because the more surface area you have, the better this is going to work. You're going to push that down in there. You can use, there should be a pipette in that box, and there's also a wire. You can use either one, kind of get it down into the bottom, but try not to crush or mash all the fibers together. You want to keep it kind of fluffy. Then you put in the metal piece, and then there's a blue top that screws into place. I don't know where the blue top went for this one. Oh, here it is. Yeah. This will screw into place. All of this is attached on the other one. So you screw this on, and then you just slam this down. Now, it generally works best the first time. This, again, is a 2-person sort of job, because if you're the one slamming it, it's kind of hard to see what's going on down here. So have other people looking at that. We've had a couple of people manage to get a fire. I usually can only get smoke. I think that's a matter of how hard you slam it down. So you can try it a couple of times, but that does tend to be the one that is sort of the rate limiting step for our experiments, that people finish the other ones and they're just waiting around for the fire syringe. So, don't try it a million times, but you can try it a couple. So did you get any fire, just smoke?
He got fired.
Excellent. Anybody report it?
No, I'll go into this time.
Okay. I need somebody to record it so I can see. I've never actually seen the fire. Pull that out.
What laws demonstrated?
Yeah, I saw
Had changed the pressure. What did? That's right.
Do it over here so that.
Brett, do you want to record it? Or I don't think
Alright, so you guys have done this a couple of times?
we're about to record it.
Okay.
First time. Ready?
Definitely saw smoke.
Yeah, you got fired. One thing we'll be able to do right.
All right, when you are done with that, this table needs the fire syringe. All right, so this was a lot bigger when it came out of the microwave. It's flattened now, but heating it made it big. You guys done with yeah, we should do the fire. Okay. All right, just give it back to them. Do you need another one?
What? If you go on the
I mean, it's still getting bigger.
Okay. Pressure, temperature is held constant.
Yeah.
Well, you guys don't have a little floor. Oh, you have the uniform. Yes, watch the uniforms on.
Y'all wanna do it? It don't matter to me.
Did you see it?
Yes. She can see it. Come on.
Are you guys done or do you have anybody else?
Huh? Maybe I didn't have those. Oh, yep.
We used to have 3 of these and one of them lost an eye when we did this, so it didn't work anymore. Some of the toys, instead of being like this, they're more rigid, but then the eyeballs will come out. I'll show you one in just a second. And so when you pull it out the eyeball. Spin. This guy. Doesn't do it too much like
Not really.
Yes.
Yeah. Any? I don't think that's anything.
All right, so there's a couple things that I want to go over. So first of all, on the back of your paper, there is not the individual, but the group paper, there's the question about what's happening with the particles. So I always think it's a good idea to be thinking about what's happening with the individual molecules. So this is kind of the sketch that you have, and we've got the pump hooked up here, the air is coming out, we're pulling the air out. So what happens to the molecules that are in here? Are we increasing the number in here? Are we decreasing the number in here? Increasing?
Decreasing.
Decreasing, okay, and are they coming from inside the balloon, outside the balloon, or both? Outside. Just the outside part of the balloon. So if I were gonna draw my scenario number 2, I might have, instead of 10 dots, I might have just 5 dots, showing that there are fewer particles in it. Now, this is not good enough to get it to a complete vacuum where there's no pump. So we still have a few. All right, so what happened to your peak when you increase or when you decrease the pressure on the inside? It expanded, so we got bigger. So if this is a balloon, we're gonna draw a bigger balloon, so the volume increases. So the pressure is related to the number of collisions and how often those collisions are happening. So if I have fewer particles, there are fewer collisions, both with the wall and with the balloon. So inside I have 3, obviously more than that, but 3 molecules that are banging around in there. And at first there's a whole bunch on the outside that are banging around. And so they're kind of equal to one another. But in here, I have fewer that are banging around here with the same number banging around on the inside. So what happens to these 3? Do they leave the balloon? Do they stay in the balloon? Do I get more in the balloon? It's just those 3, okay? So we just have those 3 and they're moving around. And so as the volume is increasing, they've got a little bit more room, which means they're not going to collide with the walls as much. And so the pressure is decreased inside this balloon. Okay. All right. So the next thing that I want to look at is related to some of your homework. And that is, so a lot of your homework is just converting from one form of pressure to another, atmospheres to torr and back again. But some of it is using these laws and thinking about just in general what happens. So this is similar to something that's on your homework. So it says, what happens to the volume if the pressure is double? So you can kind of plug things in to think about it. So we might say, what if my pressure is 10 and my volume is 10? So doubling the pressure, P2 would be 20. Okay, so P1 V1 is equal to 100. Does everybody see where I got 100 from? Okay, and this is going to be equal to 20 times V2. So what does V2 have to be? 5. Okay. So we can say that as one went up, the other went down, but we can actually quantify this. What's the relationship between 5 and 10?
2.
So 5 is half of 10, right? So as we doubled the pressure, not the volume didn't just go down, it was cut in half. So if I tripled the pressure, then the volume would be 1/3. And if I had 10 times the pressure, the volume would be 1/10. Okay. Now this is for the equation where things are side by side. And another question on the back of your sheet looks at a graph that shows this. Okay, so we have this kind of a graph. And so when we have a curve shape like this, this is generally showing an inverse relationship. So as the pressure is increasing, as I go this way, the volume is going down, all right? So why do we have this graph? Is this a different situation? No. What we're graphing here is 1/P. Okay, so it's the reciprocal of P. So it turns out that if I take the reciprocal, then this turns into a nice straight line. Chemists really like straight lines because we know the formula for a straight line, right? Y equals mx plus b. And we love to do equations that involve straight lines. But this is just showing that these have an inverse relationship. Pressure and volume have an inverse relationship. All right, so let's look at this last question here. What happens to the pressure if the temperature doubles? So we have P1 over T1 equals P2 over T2. And so I'm going to take really absurd pressures and temperatures here just to make the math a little bit easier. But let's say P1 is equal to 50 and T1 is equal to 10. So it says, what happens to the pressure if the temperature doubles? So T2 is going to be 20. Now remember, this has to be in Kelvin, not in Celsius, okay? So this is really cold right here. So P1 over T1 is equal to 5. And then, that's P2. We're trying to find P2, which over 20 is equal to also 5. So that's going to be 100. P2 is equal to 100. So we took our temperature and went from 10 to 20. We doubled that. We took our pressure and went from 50 to 100. So what happened when we doubled the temperature? What happened to the pressure? It also doubled. So it's not just one goes up, the other goes up. It's a quantitative relationship. If one triples, the other triples. If one is quadrupled, the other is quadrupled. Okay. So your initial homework assignment is going to have some questions like this. And then the one that is due a few days later is going to have more realistic numbers that are plugged in. Okay. So that's just what units do you have to use, or are there no restrictions on what those units are? So no matter what the gas is, temperature is always going to have to be Kelvin. And you can tell that here because we have temperature on the bottom. So if you think about, oh, what if I have 0 degrees Celsius? What if I have a negative number? Okay, so it has to be in Kelvin. But that's where I was saying pressure and volume are already absolute scales. So as long as both sides are in milliliters, I can leave it in milliliters. As long as both sides are in torr, I can leave it in torr. Okay, so I'm not relating that to a constant. So for the combined gas law, the one with the 3 of them, I can use any units I want, except I have to use Kelvin. Okay, and then we know that that's not true for the ideal gas law. We have to use the same units that are in all, right?
That's all it's gonna go.
So I have here a, pumpkin. Okay, so I have my evaporating dish, and I'm gonna put in it some calcium carbide. And when this gets wet, it makes acetylene. So you may have heard of acetylene before. It's used in torches, like for a welder. Or a baker sometimes will use it so they can put that nice brown on the top of, say, a meringue or on top of the marshmallows or something. So I'm gonna set this in here, and that's gonna keep it dry for the moment. And then I'm gonna use hydrogen peroxide. Now, you used this in lab. You added potassium iodide to it. It turned yellow, but it also created bubbles. So this decomposes, it's H2O2. It decomposes. What do you get when you decompose? Water and oxygen, okay? So I want oxygen in here, so I will have some oxygen for my acetylene fuel. This is mostly water though, so I'm also gonna use it to add water to the acetylene. And then I'm gonna close this up here. When I get this going, it is kind of loud, so you probably wanna cover your ears. I am gonna turn off the lights though. I think it might be more interesting if I do that. And you guys that are over here might see better if you move to the back. You guys that are over there, you might see better if you move back or towards the middle or something. We have a nice glare on this. Okay, wrap that in there. Gotta give it a second. Now I've got a sparker in here that when I push the button, it just has a little electric spark. All right. 3, 2, 1. And that is how it comes in cars itself.
Wow, I need to try that.
I should have had it turned more to the middle, but it wasn't carved, yeah, or it didn't have the face out, I just didn't see that. It was
Half of it. It's half of it that comes in the
I'm sorry, say that again.
business.
Yeah, I cut out pieces, pull them out, make sure there's no strings attaching it. My first class, I hadn't cut off the strings yet, and so only the mouth came out, the eyes that were too attached. So I have to cut off the strings to make sure that it'll go properly. So, yeah, myself carving pumpkin, rather surprised to be carved.
I saw you jump.
Good job. All right, so